All right, our bell ringer question today is if a change in reaction conditions increases the rate of a forward reaction, what effect does this have on the equilibrium constant? All right, so this was definitely something that required a little bit of thought, but there is no effect if there's a reaction condition that changes to increase the rate of forward reaction because regardless of how quickly a reaction progresses towards equilibrium, the ratio of products to reactants at equilibrium always remains constant for a particular reaction at a given temperature. So today we're going to keep talking about different forms of the reaction quotient. We're going to wrap all that up today. And our learning objective is I can determine the reaction quotient of an overall reaction for forward and reverse reactions, for reactions with coefficients multiplied by a common factor, and for reactions involving pure liquids and pure solids. Just wanted to revisit this from yesterday because we're going to talk about the other three forms of the reaction quotient. Just to remind you, the reason that there are different forms of the reaction quotient is because the reaction quotient is based on a balanced equation exactly as it is written. Likewise for reactions multiplied by a common coefficient, or for reactions involving pure liquids and solids, because we're looking at the ratio of concentrations. All of these different variations and different types of reactions are going to affect how we see our Q, what our ratio of products to reactants will be. So we're going to start off by looking at the Q for a forward and reverse reaction. This one's pretty straightforward, but it's a good thing to remind yourself of and to think of. Because this is dependent on exactly how our balanced equation is written, a reaction quotient or equilibrium constant for a forward reaction is the reciprocal of the reaction quotient or the equilibrium constant of the reverse reaction. Hopefully this makes sense. But let's take a look at 2SO2 gas plus O2 yields 2SO3 gas as an example. So if we are looking at this as our reaction, so this is our forward reaction and our equation is written as such, we will see a reaction quotient. Let's call this our forward. That looks like this. We will have SO3 squared, because we have a coefficient of 2 right there, divided by SO2 squared times O2. Not squared because we have a coefficient of 1 to the first power. So this would be what our forward reaction coefficient would look like. If we were to reverse this reaction, so if we were to say we started out with 2SO3 and we were producing 2SO2 plus O2, and our reaction looked like that. So we would say that this is the reverse reaction of what we saw above, 2SO2 plus O2. Then our reaction quotient for our reverse reaction would look like this. SO2 squared times the concentration of O2 divided by the concentration of SO3 squared. So hopefully you're able to see that each of these, if I were to say that I was looking for the forward reaction and I was only given the reverse reaction, I could simply take this and solve for 1 over Q forward. And that would give me, I would simply invert what's on my denominator and my numerator, and I would get that. So hopefully this is a pretty clear relationship between the forward and reverse reactions. We're simply switching what our products and reactants are, and therefore our reaction quotient will be very different based on whether or not we're looking at a forward reaction or a reverse reaction. Let's take a look at the form of Q for a reaction with coefficients multiplied by a common factor. So if we take a reaction and we multiply all of those, all the components in our reaction, so the products and the reactants, we multiply all of them by a common factor. If this is our sample or our reference reaction, and we're multiplying by a factor of n, then Q to the n power is equal to the ratio of products to reactants raised to the n power as well. Let's take a look at what that actually looks like with a real example. So if I am taking 2SO2, this is the exact same reaction from the previous slide, 2SO2 plus O2 yields 2SO3, multiplying by 1/2. My new balanced equation will look like this. SO2 plus 1/2 O2 yields SO3. So again, because I multiplied 2 by 1/2 and 2 by 1/2, I now have coefficients of 1 and 1, and the coefficient of 1/2, because 1 times 1/2 is 1/2. So when my equation looks like this, and I know that I have multiplied all of my factors by 1/2, I can say that my coefficient, we'll call this my reaction coefficient prime 1, is equal to, and we're just going to write this out like a regular reaction coefficient, SO3, no powers, divided by the concentration of SO2 to the first power times the concentration of O2 to the 1/2 power. If we compare this, so this is our Q prime, this is like this guy over here. If we compare this to the Q of our reaction to the 1/2 power, we would see, so we're going to now look back up to our original equation and then take it to the 1/2 power. We will see that Q to the 1/2 is equal to Q prime in this instance. So Q to the 1/2, we have, once again, SO3 squared divided by the concentration of SO2 squared times the concentration of O2. All of that is to the 1/2 power. When we have power, so now we need to think a little bit again about math. When we're taking something to the 1/2 power and we're working with other powers, we can just multiply those powers when we've got powers within our parentheses that we're taking to a power. We can just multiply those. So 2 times 1/2 is going to be to the first power. That one's also going to be to the first power, but the first power times 1/2 is going to be to the 1/2 power. So when we simplify, we see that this Q to the 1/2, so the original equation, the original reaction coefficient to the 1/2 power, which was the common factor that we multiplied our reaction by, we can see that that is equal to, if we rewrite the equation, after we've multiplied all of our coefficients by that common factor. And finally, let's take a look at the Q for a reaction involving pure liquids and pure solids. This one's a little bit funky, but it's pretty cool actually, because it means we get to work with something even simpler. When we see a reaction where we have pure liquids and pure solids, we get to eliminate those terms because the concentration of a liquid or a solid does not change as a reaction involving a liquid, pure liquid or solid, approaches equilibrium. If you think about this, if you have some sort of gas that's reacting with some sort of solid in a vacuum or in some sort of container, the concentration of that solid is still uniform throughout the remainder of the solid. The concentration of the solid isn't changing. Perhaps the volume or the mass of the solid is changing as the reaction progresses, but the concentration does not. And this is where it's very important to remember that most of the reactions that we've looked at, pretty much all the reactions that we've looked at to this point, have been involving gases. When we react a gas with a solid or with a liquid, again, a liquid is like a solid, the concentration within the liquid is not going to change. The reaction quotient involving a gas reacting with a solid or a gas reacting with a liquid, the concentration of that pure liquid or pure solid is not going to change as the reaction progresses. Therefore, we can eliminate those terms when we write the reaction quotient. So let's take a look at CaCO3 solid decomposing into CaO solid plus CO2. If we were to initially write our reaction quotient just based off of this reaction as we normally would, this is what it would look like. We've got CaO, concentration of CaO times the concentration of CO2. And it should be noted that this is definitely, and we divide that by the concentration of CaCO3. None of these have coefficients greater than 1, so they all are raised to the first power. When we look at this reaction more closely, we are able to eliminate this component and this component as they are solids. And there's not a fancy way that we do this. We simply know that because these are both in the solid state, their concentrations as a reaction progresses are not going to change. So our overall Q is simply going to be the concentration of our gas, CO2. Like I said, it's different, makes things nice and simple. And let's take a look at another practice problem. This one is very similar to the ones you did yesterday, so just practicing writing that reaction quotient. We've got SCl5F, plus H2 yields S2F10 plus HCl. Pause the video, check to make sure you've balanced your equation correctly, and then pause again. Make sure you've calculated your reaction quotient correctly. So your balanced equation should look like this. 2SClF5 plus H2 yields S2F10 plus 2HCl. Again, pause your video, write your reaction quotient, check back in to make sure you've done it correctly. And here is what your reaction quotient should look like. Concentration of S2F10 to the first power times the concentration of HCl squared, because we have a coefficient of 2 right here, divided by the concentration of SClF5 squared times the concentration of H2. And there you have it.